Hello, Chemistry 10HH students. This is Mrs. Altman. We are on video number 32, Types of Chemical Reactions, Part 7. Here are our objectives for today's video. Pause here. So we're going to be switching gears a little bit. We're moving out of our double replacement acid-base sort of section of this chapter and onto redox reactions. So redox reactions, that's just short for oxidation reduction. So these are reactions in which electrons are transferred from one element or compound to another. Oxidation involves the loss of electrons, and reduction involves the gain of electrons. What I wrote there, oil rig, just helps you remember that. Oxidation involves loss, reduction involves gain. Another way to remember it is if you have a reduction in charge, you have to have gained electrons, whatever you have to do to help you remember the difference between the two. Pause here. So not today, but in the next video, we're going to get to the point where we can just look at a chemical equation and say, yes, that is oxidized, that's the oxidizing agent, that's the reducing agent, or no, it is not. But before we do that, we're going to need to learn something called oxidation numbers. So these admittedly will seem completely pointless today, and I'm not going to sugarcoat that. The reason why we need to learn how to do these is because this provides us a system of logic for determining if something is oxidation reduction or not. So right now we are just assigning numbers, sort of like quantum numbers. They seem kind of useless at first, but then you start using them, and then all of a sudden atomic theory makes way more sense. The rules just need to be memorized. There's not really any way around it. Pause here. Right, so the oxidation state of any element on its own is 0. So for example, O2, the oxidation state of those oxygens is 0. So second rule, anything that is monoatomic, so if I have Na plus, its oxidation state is +1. If I have O with a 2 minus charge, its oxidation state is -2. So oxygen is special. It doesn't actually have to be a monoatomic ion in order to have a oxidation state of -2. So for example, in CO2, which is totally covalent, the oxidation state of oxygen is still -2 here. Hydrogen is another one that it doesn't have to be ionic for this to be the case. The oxidation state of hydrogen is typically going to be +1. So for example, if I have CH4, even though this is totally covalent, the oxidation state of hydrogen is going to be +1. Pause here. So if I have fluorine, whether it's covalent or ionic, so if I have IF, the oxidation state of fluorine is going to be -1. So you cannot make this assumption about other elements when they're a part of covalent compounds, so there are type 3s. The sixth rule, it kind of makes sense because it works with the second rule. Group 1 and group 2 elements, when they're part of a compound, are typically going to have +1, +2 oxidation states, which makes sense because that's their charge. The seventh and eighth rule, that's where things get really important. So for the seventh rule, the sum of the oxidation numbers has to be 0. So for example, in CO2, the oxidation state of carbon has to then be equal to +4 because I've got the 2 -2s. Whereas here, the oxidation state of carbon has to be -4 because I've got the 4 plus from the hydrogen. And then here, the oxidation state of iodine has to be +1. And then the eighth rule, let's just say I've got a polyatomic ion. So for example, I've got CO3 2-. So the oxidation state of oxygen is going to be -2, where then for carbon, I've got X minus 3 times -2 is going to be equal to -2 because it's equal to the charge. I do a little math here. So I've got -2 plus 6 is going to be +4. So my oxidation state of carbon here is +4. Pause here. All right, I'm going to work through this. So the first one, KMnO4 minus, or not minus. Right, so the oxidation state of K is going to be +1 because it is group 1. Mn, I don't know yet, so I'm going to leave that blank. And then oxygen is going to be equal to -2. There's a couple different ways I can do this. I'm just going to set this up like an algebra problem. So 1 plus x plus 4 times -2 is equal to 0. I get that x has to be equal to +7. So my oxidation state of manganese is +7. Got P4O10. 006 rather, my bad. So phosphorus doesn't have anything known, so I'm just leaving it blank for right now. Oxygen is equal to -2. Then I set up an algebra problem. I get that phosphorus has to have a +3 oxidation state. Now for C6H12O6, carbon does not have a known oxidation number, so I'm leaving it blank. Hydrogen has one, it's +1, and oxygen has one, it is -2. So then I'm just going to solve to find carbons. So I've got 6x plus 12 minus 12 is equal to 0. I get that the oxidation state is 0. You can have 0 as the oxidation state. You're not going to get fractions as oxidation states, just so you're aware. If you get a fraction, it means you probably did something wrong. I'm never going to give you ones that give you a fraction. Pause here. Same thing here. Just going to walk through it. Right, so SR is group 2, so it's going to have a +2. I don't know what chromium is, so I'm just going to leave that blank. And then oxygen is going to be equal to -2. And I got +6 for chromium. Got NO3 minus. I don't know what nitrogen is going to be. I do know that oxygen is going to be equal to -2. So I've got that x minus 6 is equal to -1, again, because of the charge. So then x has to be equal to 5. Got HASO2. H is known to be +1. AS is not known. So I'm just going to leave that blank for right now. And then oxygen is known to be -2. AS ends up having a +3 oxidation state. And then N2, this one is pretty straightforward because it's an element on its own. Its oxidation state is just 0. Thank you so much for watching and have a great night.